9 Questions with Jason Dittmann, UF astronomer, shares his research on exoplanets. Read by Houston Wells. Before he started probing outer space to discover planets, Jason Dittmann was studying the depths of the oceans. As an undergraduate at the University of Arizona, his first research involved mathematical models of ocean circulation. But, like the gravitational pull of a celestial body, Dittmann's abiding interest in astronomy prevailed by his junior year. Now, he's an assistant professor in UF's Department of Astronomy. Dittmann's work focuses on extrasolar planets that orbit stars outside our solar system. In particular, he studies how exoplanets form and the contents of their atmospheres. Here, Dittmann explains the joys and challenges of peering into the universe, looking for new planets that can be 1,500 or more light-years away. Why did you decide to concentrate on finding exoplanets and studying their atmospheres? Exoplanet science was definitely my first interest in astronomy. I did a class project where we learned how to use telescopes and take data of an exoplanet transit. That data eventually became my first publication, so it was just that way from the beginning. In graduate school, I did one project about supernovae instead of exoplanets. That was when I discovered that I just really liked planets. Every planet in the solar system is unique with all sorts of unusual features. Studying planets that surround other stars captures that same sense of wonder in me. What does studying exoplanets tell us about the origins and nature of the universe? Studying exoplanets and their parent stars lets us understand more about our own solar system and everything in it. One thing we still don't know is whether the Earth and our solar system are common. The only way to know if we live in a rare outcome of the universe is by trying to find more planets. Of course, the search for habitable planets, and eventually life, is a part of that. So the search for planets is really a better way to understand our place in the universe. How did you get the idea to detect exoplanets that originated outside the Milky Way galaxy, and what have you found so far? Some of my current work stems from the idea that NASA's Kepler, the most successful planet-hunting space telescope, stared at a very specific part of the galaxy for 4 years. And future missions like NASA's Roman Space Telescope will look into the center of the galaxy. So people have started talking about whether different planets form in different galactic environments. My thought was, what about the galaxies orbiting the Milky Way? Those stars are way too far away to be observable, but the trick is that the Milky Way is currently eating and merging with other galaxies and has done so in the past. So there are stars, and presumably their planets, currently in the Milky Way that were born outside of our galaxy. If we look at those stars and try to find planets, we're effectively measuring the planet formation history of other galaxies. How do you determine which exoplanets are worthy of further study? The planets we want to study depend on the questions we're asking. The easiest thing to do is to look at all of the closest ones or the ones around the brightest stars. And that is a choice of convenience. It's easier to look at these planets because we get more photons, more light from the target. Otherwise, the two main things that drive our choice of target are the planet's temperature and whether it is a gaseous or a rocky planet. If we're interested in habitability, we don't want a planet that's 1,500 degrees Fahrenheit. We'll want one that's a few hundred degrees Kelvin. 300 degrees Kelvin is approximately room temperature on Earth. Or, if we are interested in Jupiter-like planets, we'll look at the biggest ones. What exoplanets have you discovered, and how much, if at all, do they resemble Earth, Mars, or Venus? I'm the primary discoverer of one planet, LHS 1140b. It's a bit bigger than the Earth, but is made out of rocks, and its temperature makes it possible that life could exist. Confirming that would be a multi-decade effort, but I consider it a very compelling target. LHS 1140b is about 49 light-years away from Earth in the Cetus constellation. Its host star is a red dwarf with low activity, making it conducive to potential habitability. Very recently, the planets in another system, known as TRAPPIST-1, are all turning out to not have atmospheres. How are you using artificial intelligence to find smaller planets that you might not otherwise be able to detect? The difficult part about finding planets is that they orbit stars. It makes it hard to disentangle the star and the planet in data. And it gets harder as the target planet gets smaller. One thing I'm doing with one of my graduate students is using AI tools and UF's HyperGator supercomputer to better remove noise from Space Telescope's data. We're essentially folding in everything we know about the star and everything we know about the telescope. Then we're using AI to try to identify small planets in the data. We've discovered a new planet with this technique, so we're hoping to expand on it and hopefully find more planets this way. What intrigued you about the opportunities at UF? The HyperGator supercomputer is a very big hammer, so now everything looks like a nail to me. If I want to try something out, it's easy to just throw supercomputer time at it and see if it's viable, and that's great. Another of the big compelling things about UF is instrumentation capabilities. There are people in the department who have built real instruments for telescopes. And that's something I'm interested in, but not formally trained to do. My graduate students are accomplishing a lot. There are opportunities here that I wouldn't have elsewhere. I know if I get an idea I want to pursue, there's almost certainly a mechanism to find support. I'll admit that when it comes to March Madness, I'm still going to root for Arizona, but there's a spot in my heart that's growing for the Gators every year, too. How might UF's new Astreus Space Institute advance your work? I'm very interested in potentially building a high-resolution infrared spectrograph with better resolution than NASA's James Webb Space Telescope. Making that happen will require a lot of resources and team support. Having a Space Institute at UF is more than I could have hoped for because it will bring together all the people and infrastructure needed to support these types of projects. Even though my work is a small part of the spectrograph project, I think there's real potential for the Space Institute to help move work from the lab and into space. Mission support is critical, and being able to have a one-stop shop for everything we might need is huge. What big scientific question propels your work? Right now, the big scientific question behind my work is, how far can we push this instrument? I like thinking about all the ways that we can take a misbehaving spacecraft and data set and fix it so that we can find smaller signals that people haven't seen before. Machine learning and AI's ability to do things like this in a nonlinear and non-intuitive way makes it possible to revisit old data sets with a new set of tools and really squeeze them for as much science as possible. There's a lot of satisfaction in taking data that are sitting there and finding something new in it. To find more stories about the fascinating research underway at UF, visit explore.research.ufl.edu.